Thank you for taking an interest in this talk. My name is Sarah Rogers. I'm currently a second-year master's student at Arizona State University, and for the past 5 years now, I have had the pleasure of serving as the project manager for a 3U CubeSat called Phoenix. In that time, I've seen this project progress from a paper proposal to a fully integrated spacecraft, which is now orbiting our planet. And in fact, this cover image was taken as Phoenix deployed from the ISS just earlier this year. Now, the mission aims to study the impacts of urban heat islands within the US using infrared remote sensing. And so in this presentation, I will discuss our mission architecture, spacecraft design, and the current status of things now that Phoenix is in the operations phase. Now, a quick overview for those of you who aren't familiar with this topic. The urban heat island effect is a phenomenon in which urban areas are much warmer than their surrounding rural outskirts, and this can generally be attributed to the overall layout of an urban area and the materials which compose it. So low emissivity materials, such as concrete and asphalt, absorb a significant amount of heat throughout the day. This is then retained and then later released, which leads to these warmer surface temperatures. As a result, when you have many buildings which are packed very closely together, using these building materials, as we see in large cities, the overall surface temperature is going to become much warmer. So the layout of the city and the building materials in it can be described by what are called local climate zones, or LCZs. And so essentially, Phoenix aims to collect thermal images of different cities within the US, overlay these with LCZ maps in order to find links between increased surface temperatures and the makeup of the urban area in itself. And in doing so, the mission aims to determine how cities can become more sustainable for future generations. So the desire to study this phenomenon, along with a student flight research opportunity provided by NASA, brought us to Phoenix. So in the fall of 2015, we proposed Phoenix to NASA USIP and received funding for it in the summer of 2016. We then spent the next couple of years developing the spacecraft until it was delivered to NanoRacks in August of last year. Now, while Phoenix aims to study the impact of UHIs, science research is actually the secondary focus of the project. First and foremost, Phoenix aims to educate the next generation of engineers on the concepts of space mission engineering and everything that goes along with it: project management, interdisciplinary communication, and generally what it is like to develop a system that is capable of completing a set of objectives. In terms of involvement, it was developed almost entirely by undergraduate students. We really only had a couple of grad students who kind of helped close things out towards the end of development. In fact, Phoenix is the very first student-led CubeSat project to be developed at ASU, and as of last November, it was the university's first CubeSat to be launched into space. So these were just a handful of key requirements necessary to complete the mission objective. Essentially, Phoenix had to be capable of imaging the city core with a high degree of pointing knowledge and control. In order to study the urban heat island effect, we really only needed to be concerned with relative surface temperature accuracy, since essentially what we're looking at is mainly the difference in temperatures between various LCZs. So these top-level requirements drove our justification for selecting our particular payload, as well as our ADCS system, and then the rest of the spacecraft bus was then chosen or developed to support that. So most of the spacecraft is comprised of commercial off-the-shelf hardware. The payload is the Tau-2 640 IR camera developed by FLIR, which includes a 100mm lens. And so we found this to be the best off-the-shelf project that met our requirements for spatial resolution as well as radiometric accuracy. Our high accuracy pointing capabilities is accomplished with the MAI 400, which provided an all-in-one system for attitude control and determination. Phoenix has one transceiver, which facilitates all uplink and downlink capabilities over UHF amateur bands. Now, this includes image downlink. As a result of that, it will take about 3 to 4 passes over the ground station in order to downlink an entire image. But this also provides a lower power and less complex solution than using S-band frequencies, which also requires directional pointing. The 3U structure, which you see, was designed and fabricated entirely by the student team. Fabrication was primarily conducted using CNCs for precision, and this also helped us to comply with the design tolerance of the NanoRacks deployer. Throughout the design process, we developed 3D printed models, which allowed us to iterate on the design before it was actually fabricated. In addition to that, this also allowed us to finalize assembly procedures as well as develop harnessing. In addition, various interface boards were developed to support data and power routing between components. So a primary interface board that's located just above the payload provides access port features such as an RBF interface, USB port, DC charging, and LEDs to indicate the on state of various power rails. Okay. So Phoenix operates in an ISS orbit, and given its mass and drag characteristics, it will be in orbit for about 2 years before re-entering the atmosphere. Now, in that time, Phoenix will be in one of three operating modes, the first of which is idle mode. That's the primary mode where the OBC is just essentially collecting housekeeping information from the rest of the hardware, and the operations team can uplink schedules and perform various maintenance activities. Then there's science mode, which facilitates all events and operations that are related to collecting science data. So during an imaging pass, the payload is first calibrated either along the coastline or to space, and then as we approach the target city, the ADCS is commanded to track the city's lat and long coordinates. And then that allows the payload to remain fixed to a particular location on the Earth as the spacecraft continues in its orbital path. Finally, an image is taken as close to on nadir as possible so that way we can get the best image resolution. The final mode occurs in the event of an anomaly. So if there is a fault, Phoenix will enter safe mode, in which operations are minimized and the team just determines the best course of action for getting the spacecraft back to a nominal state. Regarding data collection, in addition to health status and images, Phoenix will also maintain a log of events and transmit packets during critical operations such as uploading schedule files, so that way the operations team just knows that commands have been executed successfully. So Phoenix will be operated from the ASU ground station, and this will serve as the primary interface for all uplink and downlink of the spacecraft. So the full communications path is shown in the lower right image. And essentially, the ground station antennas are mounted to a rotor system. So when Phoenix comes within range of the ground station, the antennas will track Phoenix as it passes overhead. Any packets that are received by our radio are then passed to our TNC. The TNC then demodulates the signal and strips the KISS protocol before that packet is then sent to our ground station and processed further from there. Control of the rotor system, as well as any Doppler shifting effects that occur to the frequency, is handled by two software called gpredict and hamlib, both of which are open source and widely used for tracking spacecraft. And then the gpredict interface is shown in the top right there, where you can see the antenna and radio control on the left, and then the satellite's orbital path on the right. A few additional resources that were extremely helpful in preparing for the operations phase were the amateur radio community and the SatNOGS database. Now, SatNOG stands for Satellite Network of Ground Stations, and essentially what this is a network of amateur radio ground stations, an international network of ground stations distributed all across the globe, and an associated community of operators which assists in tracking spacecraft. SatNOGS also provides a database for observations, which includes waterfall plots, audio files, and even decoded packets. And so, since there were so few passes per day over the ASU ground station, these resources were significantly helpful to us in monitoring Phoenix when it was not over ASU, to make sure that it was okay and even debug events as they occurred. So, after many years of development and additional months of preparation, Phoenix deployed from the ISS on February 19th of this year. So several members of the team gathered at ASU in order to watch it at a very lovely time of 2:30 in the morning. But then again, we are all college students and we don't know what sleep means anyway. And 30 minutes after Phoenix was released and we deployed its antennas and initialized our health beacon, someone heard from it. This very enthusiastic small child in the bottom right pretty much encapsulates our reaction. So the left image there is the very first health beacon that was received by the SatNOGS database, and this is just one of many that was received by ground stations located all around the world throughout the course of the day. We even received packets at the ASU ground station, which is shown on the right there, and we were even able to uplink a simple schedule file and confirm that it executed, which you can see in that top right image there. So to start, everything was going very well with the operations phase. It was very exciting. So where are we now? Now, despite the initial success of Deployment Day, Phoenix did experience an anomaly where a flood of packets were transmitted from the spacecraft before the battery drained below its voltage threshold. Later, we found that the satellite was able to recharge and that it was still capable of two-way communications, but we were no longer able to receive health beacons, and our ground commands did not work. The OBC still proved responsive, but only to short pings. So investigations into the packet stream found that this was caused by a communications protocol called RDP, or Reliable Data Protocol. And so this transmits SYN and ACK packets to ensure that there is a proper link between the spacecraft and the ground station before any actual data is transmitted. If nothing is received, it will continue to transmit these packets until it gets a response. Now, we didn't intend to use this protocol. It wasn't incorporated into our ground station software, so there was nothing to properly confirm a link, and the spacecraft just kept transmitting. This created an increase in power consumption, which led to the battery to drain below its voltage threshold. Through further research, we were able to determine that RDP was enabled due to a bit flip in the uplink. So in our packets, there's a flag section which indicates which indicates the CRC checksum, as well as whether RDP is enabled. Now that bit flip caused the spacecraft to think that we were using this protocol, which in turn led to this packet flood. And so really this was just something that we weren't able to catch during our systems level testing. Now, while we've been able to resolve the cause of the error packets, we don't fully understand why the OBC is only responsive in a limited manner, at least not at the time of recording this. However, we do have a few theories as to what may be going on, and these are currently under investigation. Now, despite the current situation, the fact that Phoenix deployed and that we heard from it is absolutely incredible. And really, it's in the sense that the primary mission objective was achieved. Further, we were still able to get a lot of really incredible experience in operating the spacecraft from orbit, and just learning what the early days of operations for CubeSats are like. And that will go along to help future CubeSat missions at ASU. Some additional good things are, since Phoenix is technically still responsive, it can be used for calibrating ground stations. And if you're interested in transmitting to Phoenix, I encourage you to go to our website and you can find instructions on exactly how you can do that. UHIs will still be explored by our science team, but these just using Landsat images as opposed to our own data. And this does not diminish what they would find at all. They're really just using a different data product, which offers a slightly higher spatial resolution than what Phoenix would have provided. Ultimately, many good things have come out of this project. Not only has it taught us so much, but it has also opened the door for additional CubeSat missions at ASU. And really, myself and the rest of the team are just more than happy, more than anything, have been incredibly happy to have had this ride that we've gone on over the past couple of years. Now, if you're interested in learning more about Phoenix, there are a couple of ways that you can do so. The first of which is our website, and this details much of which has been described within this presentation, but it also houses various documents that were developed during the project and other resources that we used. And hopefully this can just be useful to people who are interested in how other teams were structured or developed resources or just worded things in applications. The second resource is a podcast. So over the course of the summer, I decided to jump on the podcasting bandwagon and have developed something which explores how payloads and spacecraft are developed and the lessons learned along the way. Now, there are a few episodes on Phoenix, one on our flight software and just lessons learned throughout development and testing, and then another on structures, flight integration, and delivery, the latter of which includes our infamous story on how Phoenix was saved by Capped on Tape. So that episode comes highly recommended. The final resource at the time of recording this is not done, but is meant to be a comprehensive history on how generally Phoenix was taken from a paper concept to a flight system. And so that just hopes to highlight our experience in working on the project and show what that was like to people. So with that being said, that's Phoenix. If you have any questions on any of our resources or anything in this presentation, please feel free to reach out to us on our website, or you're more than welcome to contact me directly. We will be more than happy to help you in any way that we can. Thank you so much again for coming to this talk, and I hope you enjoy the rest of the conference.